Good morning. My name is Preetham. I'm a student of the University of Texas at Arlington, where I'm pursuing my master's in computer science. The paper I'm about to present is actually an extension of the final year project I did during my undergraduation at Amrita Vishwavidyapitham, Coimbatore. So let's get started. The paper I'm about to present is titled as Estimation of Rainfall Quantity Using Hybrid Ensemble Regression. Before I get into the details of the paper, I'd like to first introduce the other authors from the paper. Harshavardhani Vasu, she was a student at Amrita Vishwavidyapitham, Coimbatore, and she's currently doing her MS in computer science at the University of Texas at Dallas. Mr. Dayanand Vinod, he was a project supervisor at the university. In this presentation, I will be going over the following things: abstract, introduction, related works, process flow, results and discussion, and the conclusion. In this paper, Ensemble methods such as bagging and boosting are used to predict rainfall in districts belonging to Tamil Nadu, India. The Ensemble regression models are optimized by tuning the parameters such as number of estimators, base estimator, and the maximum depth. Based on the initial analysis, it was concluded that the bagging regression performed better than the other ensemble regression models, but the difference was very less. In order to enhance the performance of the ensemble regression models, ensemble techniques such as simple averaging, stacking, and blending are used, where the ensemble regression models are combined in various combinations. This model was called as the hybrid ensemble regression model. The developed models are compared by visualizing the predicted results with the true values. So, why rainfall prediction? Rainfall actually plays a crucial role in the lives of every organism on the planet. It helps in maintaining the vegetation, improving the groundwater table. Groundwater table. Recently, there has been many cyclones in the southern part of India, which has taken a lot of lives and damaged a lot of properties. These cyclones have cost government millions and millions of dollars to repair the damage. So, if rainfall can be predicted, it will help both the government and the public. So these are our contributions in this paper, which was actually mentioned in the abstract previously. The dataset description. The dataset used for the prediction was downloaded from the India Water Portal metadata repository. The dataset consists of the following independent attributes: average temperature, cloud cover, maximum temperature, minimum temperature, crop evapotranspiration, potential evapotranspiration, vapor pressure, and the wet day frequency. And the dependent attribute that is the attribute that is used for prediction is rainfall. The algorithms used for predicting rainfall are multiple linear regression, support vector regression, distinct tree regression, and the polynomial regression. And the ensemble techniques used for predicting ensemble techniques used for combining the models are simple averaging, blending, and stacking. The advanced ensemble regression models used are random forest regression, extra trees regression, bagging regression, gradient boosting regression, and extreme gradient boosting regression. The error measures used for evaluating developed models are mean square error and the explained variance score. So, the process flow. As mentioned before, the data was collected from the India Water Portal metadata repository, and all the districts data was combined. Since each column had different ranges, and the columns are normalized using the min-max normalization. This was a data pre-processing that we used, and the process data was sent to the ensemble regression models, where empirical analysis was performed to find the best possible estimators for each of the model. Now, the predicted result of these ensemble regression models are sent to the ensemble techniques, the simple averaging, stacking, and blending. And the ensemble regression models and the hybrid ensemble regression models, the results are compared using the actual rainfall values. So, first, the number of estimators optimization. The process has been done for all the models, and the result for RFR, random forest regression, with MSE as a performance measure is shown in the below figure. It can be observed that as the number of estimators increases, the MSE value decreases. But after the value of 100, the MSE value stays stagnant. So we can actually take the number of estimators as 100. And in this figure, it is actually the RFR performance is evaluated with the help of explained variance score, and it ranges from 0 to 1. And it can be seen that as the number of estimators increases, the value of the EVS increases, but as mentioned before in the previous figure also, the value after 100 doesn't change much, so we can actually use 100 as the number of estimators. This same process was actually performed for all the other ensemble regression models used and is shown in the table. And it can be clearly observed that RFR with number of estimators as 100 performs better than the other models in the current scenario. Similar to the previous optimization, now we are actually performing maximum depth optimizations on the RFR with MSE as a performance measure, and the results are shown in the previous below figure. And it can be observed that after a maximum depth of value 9, the result doesn't change much. And here, the number of estimators is chosen from the previous table in the previous slide. Now the same thing is shown for the EVS, and it can also be observed here that the EVS doesn't change much after 9. It can, if you can notice here, the EVS graph and the MSE graphs are mirror images. That is like for MSE, the minimum the lowest possible value is the best model, and for the EVS score, the more the value, the better the model is. And similar to the number of estimators optimizations, we have actually performed the maximum depth optimization for all the other models except for the backing regression, because there is some maximum depth parameter for that model, and it can be observed that GBR with maximum depth of 5 is performing better than the other models in the current scenario. Now, as mentioned before, the backing regression doesn't have maximum depth, but it has another parameter called as a base estimator. And now the base estimators are plugged in here, and these models, the multilinear regression, decision tree regression, and polynomial regression of 4, and support vector regression with kernel as linear, these models are actually chosen from our previous paper titled Forecast of Rainfall Quantity and its Variation Using Environmental Features. And it can be clearly observed that in the previous paper, the polynomial regression at degree 4 outperformed all the other models, and similarly here, bagging regression with base estimators polynomial regression at degree 4 outperforms the other models. But if you notice, the MSE values in this table and the previous table doesn't differ by much. So in order to enhance the performance, the predicted results of these ensemble regression models are sent to the ensemble techniques such as simple averaging, blending, and stacking. So simple averaging is nothing but taking the average of all the predicted values that is used for that is plugged in and giving the end result. In case of blending, you have your initial data set, and that is split into the training set and the test set. And now this training set is further split into the training set and the validation set. This step is common for both blending as well as stacking, but the difference comes in the way you split the data sets. For blending, you use holdout method, or in other case, train set and test set. And in this case, we have used 90%. The blue block indicates that it's 90% of the initial train set, and the validation set is 10%. And the trainings, ensemble regression models are trained on the blue block, and the tested on the yellow block, and the predicted results of these yellow block are chosen for training the further models. Same thing here. In stacking, again, the validation technique used for splitting the data set is k-fold cross validation, where k is 10. And since you have a k-fold cross validation, 10 times you get the execution is done, and you have 10 different set of data sets. That is like if you have 100 rows, and initially the first 10 rows will be the test set, and the other 90 rows will be the training set, and based on those 90 rows, the 10 tuples will be predicted, and the results will be stored over there. That is like it's done in an iterative fashion. And here we have made a small modification to the current stacking. That is, instead of just using the k-fold cross validation, we have also used a repeated k-fold cross validation. That is like where the repeats is 10. So the total number of iterations would be like 100, and that would go for a mammoth data set in the end. So all the results are combined or compare, compared, and the results are shown in these tables, where the comparison between the hybrid ensemble regression models are using MSE shown in this table, and in the next slide we have the same, this one with EVS. It is quite difficult to interpret from this, so we have actually chosen the best models from each of the categories, that is from simple averaging, blending as a whole, stacking with repeat 1, that is the k-fold cross validation, stacking with repeat 10, that is a repeated k-fold cross validation, and are displayed in this table. And it can be clearly observed that stacking with repeat 10 performs, that is the modified stacking performs better than the original stacking, and is performing 2 times better than the simple averaging. Now, the best model from this table, that is stacking with repeat 10, where the models uses polynomial regression degree 4, is then compared with the other best models, that is like for ensemble regression model, we have the best model as a bagging regression with the base estimators polynomial regression with the degree 4, and from our previous paper the polynomial regression degree 4 and the true value, and it can be clearly seen that the red line, that is a stacking line, is very much in correlation, that is in correlation with the blue line, that is the actual line. And if you look at more closely, it is actually in more it is actually more closely compared to the other lines. Now, since from the graph it can be clearly observed that the stacking is the best model, now this model is compared with the other models, other papers that have used the same data set, and the analysis is shown here. The first two papers are other authors' papers, and the third paper is our previous paper as mentioned before, and this proposed model in this paper actually performs twice in terms of MSE and is providing 11.1 increase in the EVS values, which is a great improvement in terms of variance. So it can be concluded that our proposed model is actually performing better than all the other models, best models from other papers. And this is the conclusion that we arrived at, as mentioned before. That is the final model, that is the stacking with repeated k-fold cross validation, where the base models are extra trees regression and bagging regression, where extra trees with number of estimators as 90 and maximum depth as 11, with bagging regression with number of estimators as 70, with base model as polynomial regression degree 4, which was the predicted results of these two models are fed into the polynomial regression degree 4, and that in turn gave the best model, which performed better than all the other models, as well as the other best models in the other paper. These were the other references that we have mentioned in the two slides before this slide. So thank you.